Hi, thanks for coming to my talk. I'm Yuping Lin from Colorado Boulder. Today I'm going to talk about the chiral multifold fermions, where we see a dual Haldane sphere and the correlating quantized band geometry. The content of this talk has been included in the archive paper below, and the work has been done with Weihan Xiao, who just got his PhD from Chicago. So what are chiral multifold fermions? They are the low energy excitations at the topological nodes in the Brillouin zone. The low energy theory for these topological nodes could be described by the k dot s Hamiltonian. Here k is the momentum and s is a spin which could be either half integer or integer. The number of bands are determined by the spin and the dispersion could be either linear or flat. An important thing here is that the bands could carry non-trivial topology. That is, if we look at a single band in a system, there could be a Berry monopole charge at the band crossing, and the monopole could give rise to the Berry flux, which comes out from the monopole. And if we do a surface integration around the monopole, we could get the integer Chern number, which is twice of the monopole charge. We note that the integer Chern number is independent of the surface integration, and it is called a topological invariant accordingly. So these have all been well-known results. We want to see if there are more interesting things in the band properties. To do this, we go back and look at the formalism of the band geometry. If we look at an eigenstate and measures the variation of it in momentum space, it is described by the quantum geometric tensor. There are two types of variation here. The first type is the phase variation, which is measured by the imaginary part and is corresponding to the Berry flux. The second type of variation is the state variation, which is captured by the real part of the tensor, and it is known as the quantum metric or the Fubini-Study metric. It measures the quantum distance, which is the state variation under an infinitesimal momentum transfer. So we want to calculate the quantum metric for the chiral multifold fermions. To do this, we need to first know the wave function for it. We look at the Hamiltonian here, which is of the k dot s form. It has the spin-orbit couple rotation symmetry. So we know that the eigenstate should be described by monopole harmonics and the spin eigenstate. If we plug in the monopole harmonics wave function to the calculation of quantum metric, we immediately see that the trace of it will be quantized and labeled by the spin and the monopole charge. If we further do a surface integration, but now excludes the double counting along any axial direction, we'll get again a quantized result. And furthermore, it is independent of the surface integration. Independent of the surface of choice. So we call it a geometric invariant. Note that the geometric invariant is protected by the rotation symmetry, as it comes from the monopole harmonics wave function. If we replace the monopole charge by the Chern number, we'll get the sum rule between the geometric invariant and the Chern number, which is the topological invariant, and the sum is determined by the spin. Here we can see that if we have a lower Chern number, we will have a larger geometric invariant and vice versa. And the geometric invariant will have a lower bound determined by the Chern number. So how do we understand the elegant results? We could first define the position operator in the presence of Berry connection, and we rewrite the trace of quantum metric in an alternative form like this. We see that it is an expectation value of the square of dynamical angular momentum. And this form actually tells us that we're calculating a dual energy in momentum space. So we want to interpret the dual energy in momentum space in the presence of a Berry monopole charge and with rotation symmetry. To do this, we could look at its real space analogy, which is a Haldane sphere in the quantum Hall effect. So what is the Haldane sphere? It is a 2D electron gas on a spherical shell with a magnetic monopole charge at the center. Because of the magnetic monopole, the 2D electron gas would experience a Landau level quantization, which is labeled by angular momentum because of rotation symmetry, and also by the monopole charge. So we have seen the Landau level quantization in the Haldane sphere, and similarly, we could use the same analogy. We could use the same methods to calculate the dual Landau level quantization for the trace of quantum metric. We first derive the angular momentum, which obeys the SU2 algebra and takes this form. And the square of it will be determined by the spin, which is the angular momentum here. We see that if we rewrite the trace of quantum metric in terms of the good quantum number, that is the spin and the monopole charge, we will derive the quantized trace of quantum metric, which we have shown in the last page. And it means that the quantized band geometry of the chiral multifold fermions could be understood from the dual Haldane sphere formalism here. So we have seen the beautiful results. Are there any physical manifestations? Actually, there is. So the first and the most direct thing to see is that the broadening of Wannier function could be affected by the quantized band geometry. It has been shown that the broadening of Wannier function could be measured by the spread functional. Although it depends on the phase of the block function of choice, a minimum of it could be determined by the gauge invariant part, which is derived from the momentum space summation of the trace of quantum metric. And the influence of band geometry here occurs because if we have k-dependent orbital composition, we have to sum over all of the bands to get the exponential localization. And it means that a single band will be broadened because it is insufficient for exponential localization. So we want to adopt this formalism in the chiral multifold fermion systems. Here we define the region for chiral multifold fermions by a momentum cutoff. And because the trace of quantum metric is positive semi-definite, we could derive a lower bound for it by summing only in the region for the chiral multifold fermion. And this will immediately give us a result determined by the geometric invariant. It means that the quantized band geometry of the chiral multifold fermion is relevant for the broadening of Wannier function. And furthermore, if we have a lower Chern number, the lower bound for the Wannier function will be larger. And this is different from the usual understanding of topological bands. A further manifestation could be seen in the flat band superconductivity. If we look at the queer pairs which form on a flat band, because they are non-dispersive, there might be expected that the phase coherence will be obstructed. However, we know that the multi-orbital band geometry could give us a broadened Wannier function like this. So even if the queer pairs are non-dispersive, the phase coherence could still form from the overlap. And this could be measured by a finite anomalous superfluid stiffness. In particular, for the chiral multifold fermion, if we assume a constant gap function at zero temperature, we could again get the finite result determined by the geometric invariant. And again, we see that the quantized band geometry has its relevance now in the flat band superconductivity. And moreover, the result will be larger if we have a lower Chern number. It is interesting here because if we have a finite superfluid stiffness, we could have a flat band superconductivity where the critical temperature is usually expected to be higher. And finally, let me end my talk with a summary slide. And thank you for your attention.